Hello, and welcome to the second video of this video series. In this video, we will be working with a turbine and demonstrating when it reaches a maximum value of power. This turbine is at steady state and we'll be deriving expressions for its momentum energy balances as well as kinetic energy balance to illustrate when power reaches its maximum. We'll be reaching in terms of velocity, and with that being said, let's go ahead and get started. So let me explain the situation a little bit better. Of course, like I said, we have some kind of turbine here with some kind of wings or some kind of flaps or whatever that are pushing the air. We have how many amount you want, whatever size, shape. We're not focusing on that. We're focusing on the fluid going in, the area, and so on. So what did we focus on? The surface area. You can call it S. All of the surface area that the fluid touches and that goes through. And then, of course, the velocity that it goes at. Right? That gives us the volumetric flow rate. However, since we're working with momentum energy balances, we want this in a mass flow rate basis, so I'm going to multiply this simply by the density, and that gives us that. And then, of course, we have something going in. I'm just going to write a circle here. We have something going in, of course, that leads into this turbine, right? It has also some kind of area. I'm going to call it A1. Of course, it's going at some kind of velocity, and we're going to call that V1 as well. And of course, it has some density, but the density remains the same, so just kill that row. Of course, same thing here on the right-hand side, but obviously this is much bigger, as you may think. The kinetic energy gets kind of used up here on the turbine, and therefore the velocity will be also much smaller, and in turn, the area has to be much larger in order to compensate for that, right? So something going over here, and of course we have A2, call it V2, of course, and then rho. And that gives us the mass flow rate on the second instance. Of course, what I said earlier, we want to illustrate when power reaches its maximum, dealing with its velocities, and how we're going to do that is in ratios, and more specifically with Betz's law. We'll be illustrating that Betz's law is true here, and that what that means is that we're going to be looking for this value r, and what that is the ratio between the two velocities of v2 to v1, right? To illustrate the ratio over there. So with that being said, let's go ahead and get started. I'm going to start off with a momentum balance. So the change in momentum in the system over time, change in t. What is that going to look like? So what we have going in, so we're going to have V1 multiplied by, I'm going to say m dot as for the mass flow rate, and then out we have V2, and of course mass flow rate 2, right? And then of course we have to compensate of the force that is acting upon the blades, right? And then of course, like we've already stated, this is, we're imagining this to be a steady state. Of course, with anything at steady state, anything with respect to time goes to 0. Nothing changes with respect to time. So this is negligible, or we can think of it as 0. And we only have this left-hand term pretty much equal to 0, right? Because this is not existent. What we can also think is the M1 and M2, right? These mass flow rates, M1 and M2, are equal to each other, right? Since we're on a steady state, these are equal to each other, and therefore we can just make that one singular one, m dot, and which is what we have here in the middle, right? The mass flow rate at the wind turbine. So we can go ahead and plug that in for our m's. So that's what I'm going to go do. So we have 0 is equal to V1 minus V2. I'm going to put that in parentheses and multiply it by rho SV, and then of course plus F, the force. Now what we're going to be doing is using the force. I'm just going to bring this back over to this side. So this becomes the negative force is equal to this expression, right? Why did I do that? Well, of course, we're solving for power, right? And we all know that power is simply equal to the force applied multiplied by the velocity, right? Very simple. So what we have to do is simply multiply this by velocity, and we don't have to get the negative value because this should be actually negative. So we're multiplying this by v because we're thinking about the force that the fluid is acting upon the fan or the individual blades, not the blades upon the fan. So for power, simply multiply this by velocity, so we get power is equal to v1 minus v2 multiplied by rho s, and then we get v squared. Right? And that's our first expression for power. So I'm going to go ahead and write it up here to the side so we can recall to it later on. Right? v1 is v2 of rho s v squared. And what I'm going to go do is erase this side, free up some space so we can go work on our kinetic energy balance system. Right. So what I'm going to do now is another expression for power, of course. And how I'm going to do that is in terms of its units. Well, we know what power is. We know that it's measured in units of watts, or also joules per meter, or also newtons per meter squared per second, and many other different ways, right? 3 different options. So we're going to be using that in our kind of power so that we can work it out. So what I'm going to do is, like I said, we'll be using a kinetic energy balance. So if we think about the change in kinetic energy, right? Change in kinetic energy is measured in joules, right? And if we divide that, or if you multiply it by the mass flow rate, which is kilograms per second, we just need to divide by kilograms, so we divide it by its actual mass. So then we get joules divided by kilograms multiplied by kilograms per second. The kilograms cancel out, so we get joules per second, which is what power is measured in. So we're all good. And of course, we all remember what kinetic energy is. We know kinetic energy is simply 1/2 of mv squared. Right? Nice and easy. So we're doing a change in that. So we're going to change between 1 and 2. Right? So we can go ahead and plug that into our expression. For power, we get power is equal, change in kinetic energy, we said 1/2 mv squared. So I'm just going to put in the difference in two velocities in our numerator. So we get v1 squared minus v2 squared all over. We get 1/2, so we divide by 2. And then we have a mass, and then we also have the mass in the numerator, so that cancels out. So we only have 2 in the denominator. And then we multiply it by the mass flow rate, which is our rho SV. So multiply by rho SV. And that is our second expression for power, right? So I'm going to go ahead and write it up here so we can refer to it later on. Okay. Now what I want to do, like I said, we want to get everything in terms of V2 and V1. So the first thing I'm going to do is make these two power expressions equal to each other so we can get an expression just for v, and then we can plug that back into one of these so that we can get an equation simply in terms of v2 and v1, right? So if I equal this to our earlier expression that we had v1 minus v2 multiplied by rho s v squared, we already see this seems very simple and straightforward. We see we have a rho on both sides, that cancels out. We see also an s, that cancels out. We see two v's, this cancels out, this becomes a singular velocity. And then we see this v1 minus v2 squared divided by 2, and this v1 minus v2 multiplied by v. So like I said, we want v on its own. We want to figure out what it is, so I'm just going to divide this on over to the other side so we can get an expression of v by itself. So we get v, and we get this v1 squared minus v2 squared divided by 2 v1 minus v2. That's our expression, right? And that may seem very easy. We know what to do next. If you may recall to algebra, or I think even earlier, maybe even pre-algebra, what v1 squared minus v2 squared, v1 minus v2, what does this imply? Well, we know that v1 minus v2 can also be rewritten as v1 minus v2 and multiplied by v1 plus v2, right? If you multiply this out, we get v1 squared minus v1 v2 plus v1 v2 minus v2 squared. That's exactly what we get, v1 squared minus v2 squared. And we can actually multiply these v1 minus v2 out so that we're ended up only this v1 plus v2 in our numerators, right? So I'm going to erase this out and plug that into here. So we get that velocity is equal to v1 plus v2, because we said the v1 minus v2 goes out, and so we are left over divided by 2. Wow, that might seem very similar, right? We're simply saying that the velocity is equal to the average velocity of these two, right? Adding them up and divided by 2, you know what that means. And this makes sense both mentally and mathematically. We can see where that is going, right? So I'm going to go ahead and put a value for v over here. v1 plus v2 over 2, which is the average of the two. And now I'm going to free up all this space, and we can start working with the change, or we can start working with r, right? So with that being said, we can go ahead and choose one of these two to plug v into. There's only a singular v here, so we don't have to square this. This seems easier, so I'm going to go plug this equation in. So power is equal to v1 squared minus v2 squared divided by 2. And then we have rho s multiplied by v, and so I'm just going to plug in this expression here. v1 plus v2 divided by 2. Right? And you can see we have some constants or some different values, so what I'm going to do is pull this rho times the s out, as well as this 1/2 out, so we can have this v1 minus v2 squared multiplied by this v1 plus v2 kind of worked out. So we'll end up with power is equal to rho times s divided by 4, right? 1/2 times 1/2, 1/4. And then we multiply this whole expression out so that we're ended up with v1 cubed plus v1 squared v2 and minus v1 v2 squared and then minus v2 cubed. Those are our expressions multiplied out. And of course, what we wanted to do is give everything in terms of v2 and v1. So what I'm going to do is multiply everything by v1 cubed. right? I'm going to pull it out to the side or to the front so that we're ended with rho s v1 cubed divided by 4 so that we're ended with 1 plus, we have v1 squared divided by v1 cubed, so we get v2 over v1. Then we have v1, v2 squared divided by v1, so we get v2 squared over v2 once, or v1 squared. That's a minus, so v2 over v1, and that whole thing is squared. And then we have a minus v2 cubed, and then that's going to be v2 over v1 cubed, and that's a minus. So there's our expression. And now, if you may see, we have everything, all 1, 2, 3 terms, in terms of r, right? We're almost there. We can go ahead and plug r into this expression so we can get everything started to looking into our Betz law. So when we go ahead and do that, we have power. Of course, we have rho s v1 cubed out front divided by 4. Now we're going to have 1 plus r minus r squared minus r cubed. All right? Yes. Beautiful. So now what I'm going to do is free up some space and we can go ahead and get started deriving this up here to get the maximum value of power. All right? Oh, I just rehearsed that equation. All right. Well, thankfully I remember it. I think P is equal to rho s v1 cubed divided by 4 of 1 plus r minus r squared minus r cubed. I think that was our expression, right? Yes, okay. Sorry, that was almost bad. Okay, so from here now, what we want to do, if you may recall, as always, we want to figure out the maximum value of power. If we think back to any calculus, we know that we can get the maximum value of power when we can get the minimum and maximum roots, right? And we can get that from getting the derivative of this expression, right? So we can find out when power is maximum due to r when we get derivative with respect to r. So we get the change in power with respect to r. We're going to have the constants rho s v1 cubed to the 4th out front. This remains the same. And we're going to have this derivative because this is multiplied by everything, because we have rho s v1 cubed divided by 4 times 1. That's simply going to be 0, so we can get rid of that. But if you multiply it by r, we know it's going to be 1. The derivative of minus r squared is negative 2r. And then we have negative r cubed, which is negative 3r squared, right? Pretty simple algebra, not too bad. Now, like I said, what we want to do is figure out when r is at its maximum, so we can get the roots of this. If you work this out, we know, what can we say about this? We can say r on this side right, we have 1 minus 3r squared. So we can do, we do a 1 minus 3r we have to multiply it by r. Is this right? We get 1, 1 plus r, or 1 plus r minus 3r, we get minus 2r, minus r times r, we get minus 3r squared. Yes, so this is the correct roots. Now we think back to what r is. R is v2 over 1, and of course it can't be negative or greater than 1. So we know that this is not possible, as this gives us r is equal to negative 1, and that's not possible. So we know that it's this one, which gives us 3r is equal to 1, r is equal to 1/3, which is Betz's law, right? That's what we saw at the beginning of the problem statement. That was our goal, to illustrate that through these derivations, power is at its maximum value when the ratio of the second velocity to the first velocity is equal to 1/3. So there you have it. Hopefully this was a helpful video, and I'll see you guys in the next one.